Hey guys, welcome to another A-level physics P5 video. And this time the past paper which we're doing is May-June 2013 P52. A student is investigating how the peak alternating current I0 varies with frequency f in a circuit containing a coil of wire. So, interesting. And the suggestion is that V0 over I0 squared is equivalent to the sum of R squared and 4 pi square F square L square, where R is the resistance of the coil, V0 is the peak voltage, and capital L is some constant. And you need to design a laboratory experiment to test the relationship between I0 and F and determine a value for capital L. And you need to draw a diagram in order to show the arrangement of your equipment and ought to pay attention to the procedure, the measurements, the variable control, the data analysis, and to safety precautions. So the way I handle such a question is that first of all, I isolate this part of it. So we know that the two variables that we are investigating is I0 and F, and so all other variables need to be constant, right? And that would include V0, which is the peak voltage, capital R, which is the resistance of the coil, and L, which appears to be some sort of a constant which we have not been given a lot of information about. So, what do we do? So we want V0, that is the peak voltage of an alternating current, to be the same, but we'd have to change the frequency of said alternating voltage in order for us to observe a change in the value of I0. I guess that is what they are saying, is it not? So how do we do that? Well, we can have either a signal generator or a variable frequency AC power supply. Both of these can work. In this case, this is a symbol of a signal generator. Right? So we can use that. In my opinion, that is our best bet. So we have managed to figure out a way in which we can vary the frequency while keeping V0 constant. So we can have this signal generator as part of a circuit which includes a coil of wire. We may draw it as a coil if we so wish it, like this or something, but it's not necessary, to be honest. And other than this, we need a way of measuring the value of the current. Now, one thing you need to realize is that because this is an alternating power supply. The value of the current isn't going to be a constant. It's going to change a lot. So we could either have an ammeter, but then the ammeter would have a deflection that would keep on changing, wouldn't it? So I would suggest that you put an oscilloscope in parallel with the qualifier, around which there would be a potential difference of V0 at one instant of time. Obviously the PD would change because an alternating voltage. So the symbol is something like this. I think I'm gonna have to double check this particular symbol. It's kind of tricky, to be honest. I'm going to have to double check this symbol, right? So on the oscilloscope there would basically be a waveform. If the oscilloscope is properly calibrated with the help of time base, there would be voltage on the y-axis and time on the x-axis. So with the help of that we can confirm the frequency. We could basically make the time period, and from that we can get the frequency and double check that it is a frequency that we set on the signal generator. At the same time we will get a value of the peak voltage, right? We can do that. And if you already know the value of the resistance of the whole circuit, we can have an ohmmeter to do that. We could have an ohmmeter also in parallel, and that would tell us the resistance of everything. That would be really cool. So we can have an ohmmeter in parallel to get the value of the resistance. And when we know V0 and we know R, we can use I0 is equal to V0 over R to get the value of the current for any particular setting of the frequency. So it's not all that difficult to ensure that R is the same, because if we use the same apparatus each time, it's gonna be the same. We're gonna change the frequency generated by the signal generator while keeping the V0 at a particular value, and hopefully the V0 will be a bit big, because I0 is equal to V0 over R, isn't it? The expectation is that it's going to be different, because we want V0 to be the same, and if R is the same, how would you expect the value of I0 to change? So whatever method that we were previously utilizing seems to be redundant. This method has failed, and this is part of the scientific procedure. When you're thinking about all of this, any way you can approach this, you're going to face setbacks. You're going to realize that something which you initially thought would work isn't going to work, and that is why I suggest, and this is a hard lesson, that you complete your thought process before you start writing. Even if you feel a bit panicked and you want to get the writing process over with, you can avoid a big mistake. So this isn't the way to go with it. A better idea would be to simply have an ammeter, and even if the deflection is a bit big over here, to keep an eye out for that one moment in which it is at its highest value. Note it down, and you're going to get the value of I0, and you're going to maintain V0. You're going to have the oscilloscope, and you're going to ensure that the value of the V0 is a constant. Whatever constant you have set, and whatever value of the T you have set, you're going to make sure with the help of the oscilloscope that the signal generator is working efficiently. Or you can also use an ohmmeter to see that R is the same. I don't think it's that much necessary, but it works. And then for different values of the frequency, we will get different values of I0. right? So now that we can get to the actual process of writing down all of the stuff that we have thought up, no worries. Let's read this once more. A student is investigating how the peak, now this is important, how the peak alternating current varies with the frequency in a circuit containing a qualifier. So this part is important. And the suggested equation is important as well. R is the resistance of the coil, V0 is the peak voltage, and L is a constant. And you need to design an experiment to test the relationship between I0 and F and to determine a value for L. And from all of that, what do you get? So, number one, how many variables are there? We have V0, which is peak voltage, I0, which is peak current. We have capital R, which is the resistance of the coil. We have F, which is the frequency of the alternating voltage, and then we have capital L, which is a constant, and so we will not regard as a variable. So, which one of these is the independent and the dependent? The independent variable is the one that you're going to change in order to observe a change in some other variable. So in this particular scenario, it's going to be the frequency of the alternating current. And what is the dependent variable? It's going to be the peak current value. What about the constant variable? Any other variable except the independent and the dependent that can potentially affect the results of the experiment are considered constant. So everything else, like V0, which is peak voltage, and capital R, which is the resistance of the coil, needs to be standardized. So constant variable, peak voltage, and resistance of the coil. Now you have to remember that when dealing with constant variables, not only do you have to outline how you maintain them, how you ensure that they are the same, you have to also suggest ways in which you can monitor their values to be sure that they are, the same. And there should also be ways to see that whatever change that you are attempting to introduce into the independent variable is actually happening. Now this might be a bit confusing, it's going to make sense, maybe it already has. 15 marks, 15 distinct points. Independent variable, frequency of the alternating current. Dependent variable, peak current value. Constant variable, peak voltage and resistance of the coil. 2 solid marks. Procedure. Before that, you need to draw a diagram. We have a lot of space over here for the diagram, so it's not a biggie. You can use the space that is just beneath the question to do all of your rough working in the exams. And the thing with the diagram is, it needn't be all that neat, but it should make sense, should be as neat as you can make it. More than that, it should be reasonable, it should make sense. So this is a signal generator, and you need to label it as such. And here's the coil of fire. You should label this as well. And here's the ammeter, similarly should be labeled. And what about over here? What should we do over here? As I mentioned, there need to be ways to ensure that whatever change you're introducing is actually introduced. You need an oscilloscope. What for? It's going to make sense. So we're going to be changing the frequency while keeping the voltage output the same, and we do that with the help of a signal generator. We use a signal generator to provide a voltage output of a constant value while using the signal generator to produce different frequencies. So that is basically the purpose, the provision of a voltage output with a constant magnitude and varying, or more accurately, a constant peak voltage and varying frequencies. So what the oscilloscope is going to do, so number one, you need to know the symbol for it, for the oscilloscope. It's important, and you should take a look at all the circuit symbols that are given at the end of the A-level physics syllabus. It's going to be something like this, right? Sort of like a zigzag. And you're going to get on display of the CRO, if the CRO is properly calibrated with a time base, you're going to get a trace, right, with horizontal and vertical displacements. And the vertical displacement is basically going to be the voltage, and the horizontal displacement is going to be the time. And from the time base settings and the Y input settings, you can figure out what one block stands for. Maybe one block means 1 millisecond horizontally and 0.1 volts vertically, and from that you can figure out what the value of the peak voltage is. Actually, you already know from the signal generator, because that was the setting you put in, but you aren't sure how accurate the signal generator is, and if you're actually getting a waveform with that particular V out and that particular frequency, and from the oscilloscope you can be sure. And you can also monitor that it remains constant and does not change during any instant of the experiment. So that is the purpose of the oscilloscope. You need to have it labeled, and then an ohm meter to see what the value of the resistance is. There isn't likely a chance of it changing, but you do need to know its value. Ohm meter to the rescue. Actually, I think I drew it pretty badly. Let me redraw it with a different color. Why? Because I want to. It's kind of like the ohm sign. So if you look over here, what have we managed to do? We have managed to show how we're going to keep V0 the same, how are we going to monitor that V0 is constant, how we're going to change the value of the frequency, how we're going to see if it has changed by the amount that we intended it to change. So, is there anything we missed out? Definitely not. Have we seen a way for us to know what the value of I0 is? Definitely. We have an ammeter which is in series, and there's another variable whose value we need to know, the resistance, and we have an ohm meter for that thing. So we're all set to go. Procedure: use a signal generator to keep the value of the peak voltage at a constant value while changing the value of the frequency within a range. The value of the V out and the value of the frequency can be read from the oscilloscope to see if they have changed by the amount we intended them to change. If the oscilloscope is properly calibrated with the help of a time base, there will be a trace on the oscilloscope and there will be horizontal and vertical displacement. The vertical displacement will show the voltage signal and the horizontal displacement will show the time basically, and from the time base setting we can see what one square box represents, and by counting the number of boxes occupied by one complete waveform and multiplying by the setting of the time base, we can get the value of the period, which we can convert into seconds and then get the frequency from f is equal to 1 over t. And to get the value of the peak voltage, we can figure out the distance between the equilibration line and the peak of the waveform, multiply it by the y gain settings to get the value of the peak voltage. And after the settings of the signal generator to a particular value of frequency, we can watch the oscilloscope to see the moment that the waveform basically stabilizes. Then we can take the value of the current from the ammeter. It will be showing variation, but we want the maximum deflection of the ammeter because that is what will be representing I naught. And the value of the resistance can be read from the ohmmeter. So I have detailed both the procedure and the measurements. The variable control I have already told. Data analysis, that is interesting and something I like and dislike. So what are the objectives? We want to show the relationship between I naught and F and determine a value for L. So if you look at the relationship that we have given, so if what we're changing is basically the frequency, right? So this is a frequency. What that means is that it is on the x-axis, and so 4 pi square L square is in the gradient because y is equal to mx. And r square is then going to be the y-intercept. So what is that going to make this? We know that v naught square has literally no place being over here. So to sort of like get rid of it, we're going to have to multiply it by the reciprocal of v naught square, but we're going to have to do that over here as well. So it's going to be v naught squared is equal to 1 over I naught squared or something. It's pretty complicated. My apologies, I actually made a mistake because we really can't do that because it's v naught over I naught squared and not just the individual values. An easier way to do this is if you simply take the square root of all values, either side of the equivalency sign. That is literally the easiest way to do this. So this and this. What are we going to get? We're going to get v naught over I naught is equal to r plus 2 pi fl. So it's v naught over I naught is equal to r plus 2 f into capital L. And like I said, if f is to be one thing be independent, it's going to be on the x-axis. That leaves 2 pi L to be the gradient. right? And so R is like, is it the y-intercept? And all of this makes sense, except this one shouldn't be over here. So we'll have to do the previous statement. It needs to get over there. It needs to be like dividing all of this. So it will be basically R over V naught. So it's not R which is the y-intercept, it's R over V naught into 2 pi L over V naught into F. So 2 pi L over V naught is basically the gradient, and that leaves 1 over I naught as the y. So if we plot F on the x-axis and 1 over I naught on the y-axis, and we get a straight line which does not go through the origin, then this relationship is valid. And the second thing we need to do, we want to get the value of the L. Easy. We need to take the gradient of the graph, right? And whatever the gradient is, we're going to have to multiply the gradient by V naught and divide by 2 pi to get the value of L. V naught is a constant, gradient is what we're going to find out, and we're going to get the value of L. Any sort of safety precautions? I'd say all of the wiring, everything needs to be properly insulated, and because there's current going through, the wiring is likely to be heated. So even after the circuitry is touched off, please do not touch them without any gloves. You might end up burning your hands slightly. So let's see how we did. See, F is the independent variable. Yes, I naught is dependent, and we need to keep V naught constant, 3 marks scored. We need a labeled workable circuit diagram of operators, including coil connected to either power supply or signal generator. Done. Variable frequency AC power supply or signal generator. Yep. Measure current using ammeter or PD across resistor. Done. Measure V across power supply or across the coil. Example, voltmeter or CRO explained. Done. Measure F using oscilloscope. Read off the signal generator. Done. Plot the graph of 1 over I naught squared against F squared, or V naught squared over I naught squared against F squared, or equivalent. I believe we did something similar. I think our method would have worked as well. They chose not to take the square root, but I find that it would have made calculations easier. Recent method prevent overheating of the coil or burns from the coil. Done. Use low frequencies to produce larger currents. Yes, you can actually see that from over here, that because they are inversely related, in order to get a big value of I naught, so there would be less percentage error, you'll have to use low frequencies. Keep resistance of the circuit constant. Done. Additional detail on measuring T using time base. Done. F is equal to 1 over T. Done. Additional detail on measuring V naught using Y gain. Done. Relationship is valid if straight line provided plotted graph is correct. Done. Is valid if straight line does not pass through the origin. Detail on changing RMS to peak. Done. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. If you wrote this, you're probably going to get full marks. And this is the way to go, because the next question has a lot of graphical work and sometimes you lose marks, but you can also score well on it. The thing is, basically, spreading your time out evenly and doing one that you are most likely to get full marks in first, because sometimes the time isn't good enough and you want to maximize your marks during the exams. Hopefully you found this helpful. Thank you.